Hi to all. Today's topic is Lenz law. In the previous lecture, I explained about the Faraday's laws. In that Faraday's law, we got that is second law is induced EMF is equal to negative rate of change of magnetic flux. Induced EMF is equal to negative rate of change of magnetic flux. In this, the negative sign importance explained by the scientist Lenz law by importance of negative sign explained by the Lenz, by his law, that is Lenz law. Now, what is Lenz law? The polarity of induced EMF. Polarity means direction. The direction of induced EMF. The direction of induced EMF or the direction of the induced current always tends to oppose the change in magnetic flux. That means now here it is the EMF is inducing. This induced EMF minus indicates opposes this d phi change in magnetic flux. By the formula you can remember the Lenz law also. Induced EMF opposes change in magnetic flux. Look at here, this is the induced EMF and minus indicates opposes, d phi is the change in flux. Induced EMF or current develops in a coil, right? That developed current opposes the change in magnetic flux. Right. And now I will explain one clock phase rule. What is the clock phase rule? For example, if you take any loop, in that if current passes, then if the current is in clockwise direction or whatever it may be, clockwise or anti-clockwise, then we have to, current carrying loop behaves like magnet, then we have to use the clock phase rule to find the which phase act as north and which phase act as south. Let us see here. Now, when you take any one loop, the phase which is the phase of the loop which is towards you, if it in that phase, if the current appears as clockwise, this is the phase, for example, phase of the loop, one phase of the loop, and other phase is that side. The phase of the loop in which if the current appears as clockwise, look at here, right, then that phase will act as south, and if the current is in clockwise, then this phase act as south and the other phase will act as north. If the current is in anti-clockwise direction, then that phase will act as north. That means current carrying coil behaves like magnet, and one phase of the coil act as north and other phase will act as south. Let us see the Lenz law importance. Then the Lenz law is used to know the direction of induced current. When current will be induces, that is, when you will change the magnetic flux link with a loop. For example, this is a current loop. Let us consider this is a ring or the current carrying wire. It is in the shape of circle. Right? When you will move the magnet either towards the loop or away from the loop, then at that moment the magnetic field link with this loop and the magnetic flux link with this loop changes. Then the change in magnetic flux induces EMF and current in this loop. Right? Then that is according to Faraday's law, induced EMF is equal to negative rate of change of magnetic flux. Now, the Lenz law is used to know the direction of induced current. Let us see some examples in that how it will shows the direction of current. Let us see here. This is the first example I am going to give. That is, this is a loop. This is a loop. And here we are taking one magnet, that is the north pole of the magnet. I am moving the north pole of the magnet away from this loop. In this loop there is no battery and actually there is no current. This is a wire, insulated wire that is made like a loop, right? Loop means just closed. And now when we will move this magnet, right, I am moving the magnet towards the loop. When you will move the magnet towards the loop, then the field will be increases and the flux will be increases. Right? Then that flux should be decreased. The flux should be decreased. then in order to decrease the flux, here the opposite field should be generated. That means the phase which is towards the north, it will act as again north phase. Then when you will move this north towards the loop, then this north repels motion, then that's why here the current will be generated like an anti-clockwise direction. This is the direction of the current. Okay, direction of induced current. That means when you will move the north pole towards the loop, then on that also the phase of the loop which is towards the magnet again act as a north pole. Then it will not allow to move the magnet. That means the magnet motion will be decreased, opposed. Magnet motion opposite means flux also opposite. Actually, how the field is changing? When you will move the magnet, the distance decreases, field increases, because you know that the field on the axis of the bar magnet, right, it is the inversely proportional to r cube. In case of short bar magnet, the field formula is u0 by 4 pi into 2m by r cube on the axial line, b inversely proportional to r cube, and the flux formula is ba cos theta. Then we write the flux is proportional to field. If the distance decreases, when the magnet comes close to the loop, the field increases. Distance decreases, the field increases. When field increases, automatically flux increases. Then the flux should not increase. The change in flux should be opposed. The increase in flux should be opposed. That's why the opposite flux should be generated. This side the lines should comes, right? Then this side field should be generated. Means when you will move the north pole, then on that phase north will be forms. Let us see the next one, and one more example. If the I want to okay, let us see for the another example, that is example 2. The example 2 is that here the same coil or the loop but what I am doing it here, I am moving the magnet away from the loop. This is the magnet, but I am moving the magnet away from the loop, right? When we will move the magnet away from the loop, then what happens? How the current will generates in this loop, right? This is the situation like this. This is the loop, this is the phase that you are looking, and now this is the magnet. The magnet is moving like this, either moving towards the loop or away from the loop. In this phase, how the current will be produces, right? When we will move the magnet away from the loop, what happens? Then the field will be decreases. When you will move the magnet away, distance will increases, and the field decreases. When the distance increases, automatically field decreases. Then when we will move this magnet away, then the flux link with the loop decreases automatically because of decrease in field. When the flux decreases, the decrease in flux should be opposed. Decrease should not occur. For that purpose, what happens? How the field is decreasing it here? Due to the motion of the magnet. That means motion of the magnet should be opposed. The flux is decreasing due to the motion of the magnet. The motion of the magnet should be opposite. That means here south pole will forms. When south pole will forms, then this south attracts the north, not allows to move away, right? Then when a motion is opposite, at that moment automatically the change in flux also opposite. Then in such a way that here south pole forms, that means current will be generated like this, right? This is the two examples. That means when you will move the magnet north pole towards the loop, here the face of the loop, okay, the face of the loop which is towards the north will act as north. Okay, when you will move the magnet away, right, here south forms. That means when you will move the magnet towards the loop, then this loop not allowed to move towards the loop. This north repels the north. And when you will try to move the magnet away, then that means this here south will generate, this south attracts the north. In any way, when you will try to move the magnet towards the loop, then it not allowed to move towards the loop. When you will move the magnet away from the loop, then also it will not allow because it is attracts. That means when you want to move the magnet towards the loop, then it will repels. When you want to move away, then it will attracts. That means it will always opposes the motion. That means when you want to move towards the loop, near the loop, it not allow, it will repels. When you want to go away from the loop, then it will attracts, it will not allow to move away. In that way, in this way, right, what happens, always the induced current, right, in this current will be induces in such a way that, right, the motion of the magnet should be opposite. That means the change in flux is opposite. This is about Lenz law. Let us see few examples, some more applications related to the Lenz law. And the Lenz law is the law of it is the obeys the law of conservation of energy. It is the consequence of law of conservation of energy. How it will obeys the law of conservation of energy? Let us see how the Lenz law obeys the law of conservation of energy. Right? When you will throw any magnet towards the loop, what happens? Its kinetic energy is decreasing. Right? Now let us see. Lenz law is the consequence of Lenz law is the consequence of law of conservation of energy. How it is the consequence of law of conservation of energy? Right? How it will obeys the law of conservation of energy? It was very simple to remember that here when we will throw any magnet towards this, in this the loss of kinetic energy occurs. Loss of kinetic energy of magnet. Okay, loss of kinetic energy of magnet appears in the form of electrical energy, right? When you will move the magnet, the energy is losing, kinetic energy losses, because it is opposing the motion. Due to that repulsion, its kinetic energy decreases. The loss of kinetic energy converts into electrical energy. Then after that, due to electrical energy, current passes through the wire. Then due to that, heat will generate. Means loss of kinetic energy of magnet appears in the form of electrical energy. And then it converts into heat energy. Like this obeys the law of conservation of energy. Okay, and some few questions I will give, that is, in this you have to say the direction of the induced current. Okay, right, let us see here how the current will be induces, and some applications I will give. Right, you have to carefully listen and try to understood each and every application. The first application is that let us see, this is a capacitor. Look here, this is a capacitor, this is A plate and this is the B plate. And now this is a axis. Okay, and now when we will move the north pole of the magnet, okay, towards the loop, then which plate of the capacitor will act as positive and which plate will act as negative? This is our question. Right, once try for 1 second. Okay, what happens, and which plate will act as north and which plate will act as south? Let us see for that. Then for that, what happens when a magnet is moved, north pole of the magnet moved towards the loop, then what happens? Right, the motion of the magnet should be opposite, the flux will be increases, motion of the magnet should be opposite. That means here north pole will generate Okay, north pole will generates, and when it is north pole generates, the current direction is what? This is the direction of the current. That means the current is flowing like this. That means electrons moves opposite to the direction of the current. Current is going from A to B. That means electrons goes from B to A. That means the B plate loses electrons, right? A plate gains the electrons. Electrons goes like this opposite to the direction of the current. Then B plate loses the electrons. A plate gains the electrons. That's why when we move a magnet towards loop, then capacitor A plate acquires what? Tell me. A plate acquires positive charge. Positive or negative? Current goes like this. That means electrons goes like this. This B plate loses electrons. Electrons goes like this, and A plate gains the electrons. That means B plate loses means B become positive and A become negative. Okay, A plate acquires negative charge and B plate acquires positive charge. Okay, right. Now let us go for one more example, right? And some application I will give. This is the second example I am going to give. For example, this is a straight current carrying wire. It carries the constant current. And beside of this one circular loop is there. Current, it is a loop. There is no battery, no current in this. Here in this I current passes, that is the constant. Then is there any induced current in this? That I want to know. Is there any induced current in this? Right, this is my question. Then in this there is no induced current. Why? Because here when the current is constant, then around the current carrying wire field will be generated. We have to use the right hand rule. Around the straight current carrying wire, magnetic field produces in such a way that the thumb, we have to hold the right current carrying wire in right hand in such a way that the thumb shows the direction of the current and curled fingers indicates the direction of the magnetic field. That means the magnetic field above a certain distance, here the applied magnetic field is outward, here inward and here outward, right? Like this. This is the current carrying wire, current is going right side, then this is inward field below the wire, above the wire outward field. That means outward field is indicated with the dot. Here this is the applied field is the dot. But here when current is constant, right, then applied field is also constant, right? Why applied field is constant? Applied field depends upon current, right? Then when current is constant, then the field is also constant. Applied field is also constant. Then BA is constant. When field is constant, then the flux is constant. This constant flux never produce any current. That's why induced current in it is induced current in circular loop is equal to 0. Why? No induced current in this, right? In the loop, no induced current because the flux is constant. Okay, let us see one more example, right? The same thing. Okay, the example is that this is a straight current carrying wire. In this, if the current is increasing, right, and beside of this I am placing one circular loop, right, then what happens to the induced current, whether the current induces or not? When the current is increases, then the applied field also increases it here. What is the applied field at here? Applied field is outward, then the outward field will be there. This is the applied field. Applied field is outward, right? Applied field is outward. Why? This is the applied field. Applied field is outward. Okay? Outward field will be there at here. Then due to this outward field, applied field is outward, right? Applied field is outward. And now what happens to the applied field, whether applied field is increasing or decreasing? In this case, when current increases, then applied field is also increases, right? And now I will explain. I am going to rub this and you can take the screenshot. Right. Applied field is increases because if current increases, what happens? If the current increases, then applied field increases. If current increases, right? If current increases, then applied field increases, right? Applied field increases because applied field proportional to current. Then applied flux increases. Applied flux increases. Applied flux or the flux link with the circular loop increases. Flux link with the circular loop increases. Flux link with circular loop increases. When flux increases, the flux increase should be opposite. Flux increase should be opposite. This BA is increasing now. BA is increasing it here. BA is increasing. This should not increase, right? When field increases, then the flux increases. The flux increase should be opposite. That means field increase should be opposite. Field increase should be opposite means in this circular loop the field should be generated. Due to in this circular loop current generates, and that due to that current again field generates. That field should be against to this applied field. If the field is against to this applied field, then what happens, right? If the induced field is inward, right? For example, if the induced field is inward like this, okay? If the induced field is inward, applied field here, BA is the applied field. Applied field is outward. Applied field, okay? But cross B is the induced field, right? Induced. Look at here. Induced field, if it is inward, what happens? The total field will be decreases. This is the applied and this is the induced. Induced is opposite to applied. In this field will be induces. Why? How? In this current induces because flux is changing, right? Look at here. What? Once again, right? Once again, you can look at here. Actually, we are discussing this one. This is not at here. We are discussing it here. The third point. Third point is at here. When current increases, then what happens? The field increases, right? Applied field increases. Applied field should be decreased. That's why induced field should be opposite to applied field. Applied, right? This is the applied field. This is the induced field. Okay? Induced field. Induced field, how it will be there? Right? This is the applied field. Applied field is outward, right? and then induced should be inward, then the net field will be what happens? Net field decreases. When net field decreases, then automatically our aim is to decrease the net field. That means we want to stop the change in flux. Then for that, field should be induced in cross. Then when the field should be induced field should be cross. Induced field should be cross means then induced current what happens? Cross means inward field. Inward field means the current should be clockwise. The current will be like this. This is the direction of the induced current. This is the direction of the induced current. Then the flux link with the what happens? Once again we will explain. Okay, when the current increases in the straight wire, the applied field to this loop increases. When applied field increases, then applied flux increases. But applied flux field should not increase. That means opposite field should be generated. Here already this straight wire is generating the outward field, then this circular loop should generate the inward field. Inward field means current should be clockwise. Okay, thumb shows the inward field and the current generated will be in opposite. The flux link with the circular loop increases, right? To oppose the change in flux, the current in the loop must be clockwise, right? Must be clockwise. This is answer. Okay, right. Let us go for one more. This is the fourth point. Okay, you see here, this is the straight current carrying wire. The current is decreasing, then what happens? Current is decreasing, right? This is the loop, circular loop. If the current decreases, then what happens? If the current decreases, then applied field decreases, because here if current decreases, if I decreases, what happens? Applied field decreases. BA is the applied field. Applied field decreases. When applied field decreases, then flux link with the circular loop decreases. Flux link with circular loop decreases. Look at here, the current is decreasing, then applied field is at here, will be there, applied field. Okay, what is the applied field direction? Current is right side, then applied field is outward. Applied field decreases, BA decreases. When applied field decreases, then applied flux with the loop also decreases. When the applied flux decreases, the flux is changing, then in this current will be induced. But that induced current should oppose the change in flux. Matlab, induced current should decrease the, here the flux is decreasing, applied flux, that decrease in flux should be opposed. Then to oppose the decrease in flux, then in this the flux should be generated in the same direction, because here it is decreasing should be opposed. Then if increasing should be opposed, means opposite field should be generated. Field is increasing, it should be opposed. Then for that we have to generate the field opposite to it. But something is decreasing, you have to opposite, then you have to add for that. Further in the same direction the field should be generated. That means induced field is also in the same direction, and induced flux also same direction it should be there. That means again induced field is also outward, because the field is decreasing, it should be support. Then when the induced field is outward, okay, then induced current is in anti-clockwise, right? This is the direction of induced current. Induced current is outward. Then the direction of induced current is anti-clockwise. anti-clockwise. Okay, right. Then in exam they will ask the 1 mark question. For the 1 mark question, it is no need to remember this many concepts. Direct I will give one shortcut to remember these all applications. Okay, right. I gave the third 3 applications till now, and then I will give one shortcut to remember these applications. Right. What is the direction of induced current? Then the 4th one I am going to explain. Right. Give the direction of induced current in the following diagrams. Right. Okay. Then the diagrams I will give. That the first diagram is that this is the first diagram. That is this is the direction of the current. Current is increasing. Right. This is the first question. This is A. And next, this is the second question. Here the current is decreasing. I want the direction of the current give the direction of induced current in the following circular loops. Give the direction of induced current in circular loops. In circular loops I want to give the direction of current. Circular loops. L1 and L2. There is L1 and L2. This is L1 and this is L2. Right? Okay. Now in this case the current is decreasing. This is the B diagram. And one more I will write. That is the this side. Oh, this is enough, I think. Okay, I will give. This side current is decreasing. Then what happens? See. This is L1 and this is L2. I want the direction of induced current. This is the C diagram. Okay. Very simply I will explain. Within 1 second you can give the direction of induced current. Look at here, this side current is increasing. This side current is increasing. You remember that in this current increasing means flux increasing, right? Then when the flux increases, then flux changes in this current will be induces, because the change in flux induces the EMF and current in this. Then when the current increases, then it should be decrease, then opposite current will generate here. You should remember. Here current is increasing, here opposite current will generate. This is right side, that's why here induced current is left side. Like this. Right? That means in L1 clockwise, right? L1 clockwise, induced current. And in this, here anti-clockwise. Here it is anti-clockwise, and here it is clockwise. Then what about here? Current is decreasing here. Decreasing should be opposite. When it is decreasing, it should be support. The same direction current will induces. Like this. This is going like this. Right? This is the induced current. Then what happened? Induced current. In this what happened? Clockwise. Right? In this anti-clockwise. You remember only one thing. What is that? When current increases, then induced current here near this point should be opposite. Right? This induced current should be backside. You should draw backside. Right? Backside. And here the current is decreasing, means it should be support. The same direction the current will generate. Right? Same direction. Okay? Then here the current is decreasing in the right side. when it go in the right side, it is decreasing. Current is decreasing this side. But when it is decreasing, when it is increasing, we can oppose. But when it is decreasing, what happens? When it decreases, then induced current should be support. Support means same direction current will generate. Decreasing means same direction, supports. Okay, and increasing means opposite direction. Look at here, this side increasing. Here also you see this side decreasing means support, same direction. Okay, right. And here this is the anti-clockwise, and here it is generated as clockwise, right? And this is the diagrams. Okay, and these are the questions. And one more application I will tell regarding the induced current direction. You see this diagram, and the fifth application I am going to explain, that is, give the direction of induced current. Give the direction of induced current in the following loops. Right? This is our question. And there is one diagram is there, right? Okay, like this. This is the uniform magnetic field. Uniform magnetic field. Okay, this is the uniform magnetic field, and in this there are some loops are there. Okay, there are some loops, and some of the loop like this. This is ABCD. This is ABCD. This is entering into the loop. This is entering like this. This is A. This is B. This is the C. This is the D. This loop is entering, and the next one more loop. This is in shape of triangle. It is going like this in the magnetic field. Here the uniform magnetic field is there. B is constant, right? Field is constant. And now I will give the diagram properly. Right, this is A, B, C, D. This is entering into the field. This is moving in the field. Okay, right. And one more I will take it as, this is a circular loop. It is going outside. In these three, what is the direction of induced current I want? In these three, what is the direction of induced current? Okay, right. And for this, what I have to do, right? This is, for example, this loop, when it is entering into the magnetic field, When it is enters into the magnetic field, what happens? When it is entering into the magnetic field, the flux will increases. Field will be increases. When the flux increases, which flux it is increasing? Inward flux increasing, because the field is inward. Cross indicates the magnetic field is inward. Dot indicates outward. Here when it comes into the field, then what happens? The flux increases, field increases, but that is inward flux increases, but in that increase in flux should be opposed. Increase in flux, if the flux increases, it should be opposed. If the field increases, it should be opposed. Then for that induced current and generates in such a way that it opposes the change in flux, means change in field. Okay, that means when the inward flux increases, right, look at here, when it comes into the field, inward flux increases. When inward flux increases, then increase should be opposed. That means in this outward flux should be generates. In this outward flux, outward field should be there. Field outward means the induced field should be like this, it should be there. Induced field should be dot outward. Outward means like this, right? Then the curved fingers indicates the direction of the induced current. Okay, thumb shows the direction of the magnetic field, outward field. Okay, oppose the magnetic field. Magnetic field, applied magnetic field is inward. It should be opposed, because here when it is enters, the field is increasing. That's why the current will be, right, anti-clockwise. A, B, C, D, right, like this. Okay, and now this is moving outside. This is moving outside. When it moves outside, then the flux decreases. Flux decreases. Flux decreases means it should be support. Flux, how it should be support? When it is decreases, it should be support. Means same direction field generates. Same direction means induced field will be cross. In order to support, we have to push in the same direction. For example, somebody is trying to push the car, but it is not moving. We want to support it. Then in the same direction you should push. Somebody is having the more energy and he is pushing that side. We want to oppose. If you want to oppose, then you have to apply the force against. Then here, when the field is increases, the flux increases, then in this the field generates and the flux generates in such a way that the induced current generates in such a way that the change in flux and change in field should be opposed. That means increase in field should be opposed, decrease in field should be opposed. When the loop enters, then what happens? The field increases. Okay, flux increases. That it should be opposed. Flux should be opposed. That means opposite field should be generates. And here, when it is moving outside, then the flux decreases. Decrease should be opposed. Decrease should be opposed. Decrease should be opposed means we should support it, right? The same direction field will be generates. The same direction means cross. This is the induced field is the cross. Induced field cross means what about the induced current direction? That the induced current direction is, okay, thumb shows the inward and curled finger shows the current. The current should be like this, clockwise. Simply this also you can remember. If any loop enters into the field, okay, in this anti-clockwise current will generates. Okay, induced current direction is anti-clockwise. Okay, this is the first one. For example, it is the first one, and this is the second one, and this is the third one. The second one is moving in the magnetic field only. When it is moving in the magnetic field, field constant, flux constant. Then when the flux is constant, then induced current is 0. This is the first case. The second one is, okay, moving in the magnetic field, moving in uniform magnetic field. Okay, moving in uniform magnetic field. When it moves in uniform magnetic field, no induced current, right? No induced current. And this third loop is moving away, right? When it is moving away, loop moving away from magnetic field. At that moment what happens? When field moves away, then the flux decreases. Decrease should be opposed. In order to oppose the decrease in field, it should be support. Field should be support. Then same direction field will be generates. Applied field is cross. Then the induced field also cross. In order to generate opposite, here it is there. But support means same direction should be there. Then the current is the clockwise. Okay, this is general rule. If you want, you can remember also. Entering, while entering, then anti-clockwise. While leaving, clockwise. This is for all the cases we can apply, right? In exam, they will ask the direction of induced current. Okay, this is the thing. Thank you for watching my lecture. If you have any doubt, you can ask me in comment box or otherwise in WhatsApp. Thank you.